Welcome to class for what will be the final video in our differential equations course. In this one, I want to end it with a bang and talk about modeling with systems of non-homogeneous, ODEs. Let's get started. Let's give this circuitry problem a shot. This is what we'd call an LR circuit because it has inductors, L, and resistors, R. And in this problem, we want to model the current flowing through the circuit at any given point. But really, there are three different types of currents to consider. Leaving my potential source, I have my initial current I1, which splits into two different currents that may be described different ways. So I've called this blue one I2 and this red one I3. They do join back up again into I1. I know that they add up to I1 from Kirchhoff's first law above my head here. Now, before I use Kirchhoff's laws above my head here to write down the model, first let's talk game plan. I've got three unknowns, I1, 2, and 3. So I should expect to write down three equations. Now, we're being asked to just develop a model here, and sure enough, we're gonna need to use differential equations to do it, but that doesn't necessarily mean all of our equations have to be differential equations. In fact, the first equation that we're going to write down is just an algebraic one, and it's going to use Kirchhoff's first law, that the net current through a junction in my circuit, like this one here, should be zero. And to rationalize that, it's just saying that the total current coming in is equal to the total current coming out, or that all of the current moves through the junction. So here I have I1 coming in, I2 and I3 are coming out. So I1 must equal I2 plus I3. Next up on our list, we're going to need a couple substeps to be able to use Kirchhoff's second law. Now, the second law says that the total change in potential across a closed loop in a circuit should be zero. Here I have two different closed loops. The first one being this inner loop, dictated mostly by I2 here. Leaving my source, I could travel across this resistor, then turn right, going across both inductors before returning to my starting point. The other closed loop I have is this one, where instead of turning right, I keep going straight, and then I go across both resistors and one inductor. Each loop is going to give me a separate equation. In order to be able to use Kirchhoff's second law, though, I need to understand how the potential changes across the resistors and the inductors, and those will use two other principles from physics. The first being Ohm's law, which tells me that that potential change is I times R, where I is the current, R is the resistance, and then across the inductor, we have that change is L, the inductance of the inductor, times the derivative of the current, and would you look at that, there's the differential in our equations. First thing I do is I pass over this 8 ohm resistor. I know that its potential change is equal to IR, so its full potential change there is equal to 8 times I1, because on this resistor I have the green current I1. Next, I move across this inductor with current I2, which means its inductance, being 1 Henry, gives me 1 times di2 dt. Finally, the last step is this second inductor, also with inductance 1 Henry, but this time I have current I1. So I have 1 times di1 dt. And I know that that total change, all of the changes in the potential are my electromotive force, which is 100 sine of t. Pause the video here to see if you can write down the second loop's equation on your own. Did you get it? I got the same first and final piece because that loop still includes the same first resistor, that 8 ohm resistor, and the second inductor, but this time the middle term is different because I'm passing over this resistor instead of this inductor, and it only has a resistance of 2 ohms. Now that we're done with the picture, I'm going to erase it and condense all of our math over to the other side. Be right back with you. In this scenario, the electromotive force doesn't change until it hits the first resistor in the circuit. So at that point, I have that E of t is equal to, well, it's just the current now. Using this, when I plug in 0, it tells me that I of 0 is 0. And similarly, if I differentiated both sides of this, it would tell me that I prime of 0 is 0. And here I'm using capital I to denote the vector of all of our currents. So it tells me that each current begins at 0, and its derivative begins at 0. Now I have a full system of equations that can be used to uniquely determine the currents. How would I get started with that? I think the algebraic equation is easiest to tackle. Do you notice here, I only have derivatives of I1 and I2, but both of the equations do involve I3s. It would be nice if I could write I3s in terms of I1 and 2, because then I would have a 2x2 system of first order ODEs. Turns out I can do that in a single step by using my top equation. And this is almost like the method of substitution from your college algebra classes. I'll isolate I3 to determine I3 is equal to I1 minus I2. And now I can just substitute that into my other two equations. I3 only shows up in the bottom equation though, so let me write that down. And here we have it. I3 only showed up in equation 3. When I plug it in, I now have 10I1 minus 2I2 plus di dt equals E. You'll now notice that both equation 2 and 3 are only in terms of i's 1 and 2. So I have reduced my 3x3 system into a 2x2 system, but it's now a system of differential equations. So let me clean up the board and I'll rewrite that system. Now what makes these tricky at the moment is that they are coupled, meaning that di1 dt in particular shows up across both equations. But I can very easily decouple them using another substitution. Since di1 dt is the only derivative in equation 2 as I've written it now, I can isolate it and then substitute that into equation 1. Here's what I mean. Isolating di1 dt in equation 2 gives me this expression, so I can substitute that in for di1 dt in equation 1. Now isolating di2 dt in equation 1 gives me this much simpler expression on both counts for these equations. Let me use these guys to simplify the system even further. Cleaning it all up, I can write di1 dt equals a function of only the i's and t. Same for di2 dt. By the way, we call this type of system autonomous, and autonomous systems are very nicely behaved. Writing it in matrix form, we see this is a type that we could solve through undetermined coefficients or variation of parameters.